Hi everyone, welcome to our video lesson 9.2 on exponential growth. Go ahead and grab your notebooks, your calculators, and a writing utensil, and you're going to take notes along with this video. We have about 3 questions to get through today, but before we get started, I just wanted to review a couple of quick things about exponential functions in general. We talked about in our last lesson how exponential is different than linear, because in linear functions we grow at a constant rate, meaning that we would see the same change in y values by adding or subtracting an amount every single time. With exponential functions, our growth or our rate of change is going to be different for every single step we take within our function. All right, as our x values get bigger, when we're talking about exponential growth, our increase in y values is going to get larger as well. So we're going to be seeing a pattern of multiplication in these problems. Things are going to be multiplied by 2 or 5, or they're going to increase by a percentage. And we're going to be using the general format y equals a b to the x power. And if you remember from our last lesson, a is our initial value, b is our growth rate, also known as our common ratio, and x is our independent variable. So that's the only thing that's going to stay x in these problems. Because we're dealing specifically with growth today, and we're going to separate decay and do that tomorrow, we're going to be dealing with b values that are bigger than 1. That's how our function is going to grow. Now, before we get into the questions that I created for us to go through together, I did just want to touch on how relatable this topic is to what's actually happening in your real lives right now. I know everyone loves to ask that question. Why do we need to learn this stuff in algebra? When are we ever going to use this? And I'm not saying that you guys are all going to become scientists, and hopefully, fingers crossed, we will never have to deal with one of these situations again in our lives. But as you know, right now we are dealing with the COVID-19 global pandemic, and we are all home from school because this virus is so infectious and it's growing at such an exponential rate that we need to try to do what we can to slow that growth down. And I found a really cool image online from the CDC website, which is the official website for Center of Disease Control, something like that. And these are the total number of COVID-19 cases in the United States from January 22nd, all the way through to April 3rd. Okay, now you might be thinking, why would they even include this portion of the graph? There's nothing actually going on. All right, but actually what's here in the first few spots in January, we had 1 case of COVID-19. And that 1 case is such a small number that you literally can't even see the block that they drew on their graph, because our y-axis in total number of cases is all the way in the hundreds of thousands. All right, so 1 is not even going to be a step. So we saw in our last lesson that exponential growth functions on a graph, they're going to start so close to their asymptote, you're not even going to be able to visibly see the image of the y values, because it's so close to that original horizontal line, which in this case is 0, right? But then as this started to infect more and more people, and as this infections rate started to grow, the numbers then started to climb slowly at first, but then as more people get infected, the rate of infection gets quicker and quicker and quicker until we have a growth that's almost a vertical line, right? And this is where everyone's talking about social distancing and flattening the curve, because we don't want this rate to continue to grow exponentially, okay? It can't grow exponentially forever and ever, which is a good thing, but what we want to do is we want to flatten out this curve and stop the growth rate from happening so quickly, so that we can all get back to our normal lives and hopefully never have to deal with COVID-19 ever again. All right, but I thought this was really cool to visually see what exponential growth is, and also relate it to what you guys are dealing with right now. All right, now I did a very little bit of research. I found this, but I don't know the exact numbers and the mathematical data behind the COVID-19 growth. So when I show you our first question, please keep in mind that I made this question up. These are my numbers, and this is why I did not write anything about specifically the coronavirus. But our first question does deal with a virus. So go ahead and pause the video, write down the first question as best as you can, and we're going to go ahead and get started with the solving or the writing of the function in this case. All right, so if you read through this, a virus has infected New York City. At the start, only 10 people carried the virus, but the number of infected people has doubled every week. Write an equation to represent the total number infected, V of W, over a certain number of weeks, represented by the letter W. Okay, so the important things to note here. It started with only 10 people, so there's our initial value, or there's our A of our equation. It's going to double every week. Okay, now doubling means multiplying by 2. So there is your growth rate. There's your common ratio of, I'll write it out here, times 2. So we're multiplying by 2 every single time. We're going to use V of W to represent our Y value. So instead of Y equals, I'm going to write V of W. And then our certain number of weeks, or our independent variable, is going to be represented by the letter W. Okay, so that's the important part that comes out of that question. Now, in order to do what they asked, which is to write an equation to represent the total number of infected, I'm just going to take our general exponential growth function and I'm going to replace it with all the information they gave me. Okay, Y is going to be our V of W. A is our initial number of people infected, which in this case was 10. V of W equals 10 times our growth rate, which is coming from the phrase that says infected people has doubled each week. So our growth rate is being multiplied by 2. And then our independent variable, in this case, instead of the letter X, they want us to use the letter W to represent the number of weeks. And that's it. Okay, now this equation would be used to find the total number of infected people over any certain number of weeks. So if I went to my calculator and I was curious how many people would be infected after a month, right? A month is typically around 4 weeks, a little bit longer. But let's say we went with a short month, 4 weeks. I'm going to plug in this equation. I'm going to plug the number 4 where my W would be. And my virus would go from only infecting 10 people to infecting 160 people. All right, now what if I doubled that and I went another 4 weeks, another roughly month, and I replaced that W with an 8. Okay, now I'm doubling the time. Instead of 4 weeks, I'm waiting 8 weeks, but I am not doubling that total. In 2 months, my initial virus that only infected 10 people would infect 2,560 people. All right, and you can see if I go another 4 weeks, 10 times 2 to the 12th power, we're starting to jump pretty quickly. Going from 10 to 160 was a small amount in comparison to going from 2,560 to 40,960. So that's exponential growth right there. The higher the X values, the quicker the Y values will grow. Okay. Luckily, it didn't ask us to find any specific time, so I just wanted to show you those numbers for your benefit. Okay, second question. Go ahead and pause the video, write it down, and we'll read through it together. Your starting salary at a new company is $34,000. So starting salary is $34,000. The boss explains that you will get a 2.5% increase each year. So 2.5% increase is important for me thinking mathematically. Write a function to represent your salary and use it to find your potential salary in 10 years. So that's the time that we're going to be measuring over. Okay, now, a little different from question number 1, my increase is in terms of a percentage. Okay, now that relates to exponential growth because 2.5% of a small amount of money is going to be a small amount of money, right? But 2.5% of a large amount of money is going to be a much bigger increase. So this represents exponential growth because the bigger your salary is, the bigger your pay increase is going to be. It all depends on what number you're finding 2.5% of. Okay, so when we see a percentage increase, one thing that we're going to do is we're going to change the percent into a decimal. Okay, hopefully you guys remember how to do this from middle school, but if you don't, you're going to take your 2.5%, Okay, remember that percent means out of 100. So I'm going to take 2.5 divided by 100, which is 0.025. Okay, which a lot of people like to think of the shortcut of taking the decimal place and swiping it twice to the left, which is what happens when you divide by 100. So we're going to take the decimal in its percentage form. We're going to change it to a decimal, a pure decimal, and then we're going to use that in our exponential growth function. Okay, let's stick to y equals here because they didn't give us any x or y's to use, so I'm going to stick with x's and y's. So y equals, our initial amount is 34,000. Okay, and now our growth factor is also interesting here because we're using a percentage. When you grow by 2.5%, you're not just getting the 2.5%. The 2.5% is going to be what they call compounded on top of the amount of money you already had. So if I get paid $34,000 this year, and then I get paid a 2.5% increase, I'm going to still get that $34,000 plus 2.5% on top of it. Okay, so think of it like you're getting 100% of your salary plus 2.5% more. Okay, so 102.5%. Right? Change that whole thing into a decimal, or what we like to do in algebra is when we know that it's growth, we take 1 plus the decimal that we just used, 0.025, and we raise it to our independent variable x, which in this case is going to represent years. Okay? We'll do some more practice with that when it comes to practicing both growth and decay at the same time. All right, but in general, here's our function to represent your salary. Okay, if I want to know what's going to happen in 10 years, I'm going to take our function, I'm going to plug in 10 for our x value. Okay, and then I'm going to go ahead and reach over to my left-hand side and plug in my function into my calculator. Okay. Now, what I did here is I actually mentally simplified 1 plus 0.025 and I made it 1.025. If you write it out with the plus sign, it's going to give you the same answer anyway. All right, but we get this long decimal, and if we remember that we're talking in terms of money, then we are going to get $43,522.87 if I round correctly. I'm going to round mathematically always, and that would be my salary in 10 years from now if I stuck with this job. Okay, another example of exponential growth. Move some stuff out of there. All right, the last question that we're going to get to here, Jill invests $400 in a savings bond. The value of the bond, V of X, in hundreds of dollars is illustrated in the table below, and we have two jobs. Okay, first we have to write an equation to represent the value of the bond over time, and then we need to use our equation to figure out how much it'll be worth in 10 years. Now in this illustration, we know that initially she had $400, which is why when x equals 0, we have a 4 because it's in hundreds of dollars. So this is a 400, this is $540, this is $729, right? The thing that we're missing in order to go back to that original exponential function is our growth factor. All right, so just like we did in our last lesson, I'm going to actually try to figure out how do I get from 4 to 5.4 using multiplication, or how do I get from 5.4 to 729 using multiplication. Not very easy to do mentally, so let's go ahead and use our calculator. I'm going to take 5.4 and divide it by 4. And I get 1.35. Okay. The cool thing is if I chose any of these, 7.29, and divided it by the one before it, 5.4, I get the same 1.35. Okay, that's because x is going up by 1 every single time, and my growth for this exponential is going to be, my common ratio is going to be 1.35. Okay, so if I use the $400 that we started with, which we're going to use a 4 because V of X is in hundreds of dollars, and the, I don't know why I'm writing in green, and the growth factor, which we now know to be 1.35 raised to the x power, that would be the function of our value over time. Okay, now the cool thing here, and I just want to relate it back to what we did, we saw 1 plus 2.5% as a decimal, right? This would be 1 plus 35% as a decimal. So they could have told you about this savings bond by saying she started with $400 and she gets a 35% increase each year. Okay, that's what this 1.35 is telling us about her savings bond. Okay, now how much will it be worth in 8 years? Well, go ahead and plug in the 8. V of x equals 4 times 1.35 to the 8th power instead of the x power. And even I'm going to come over here and plug that in. Okay, and I get v of x equals 44.1296158. Oof, long decimal. Okay, now remember v of x is in hundreds of dollars. So the number 44 is actually going to relate to 4,400. So this, if I go ahead and translate this over to how much money she's going to have in her bank, this would be $4,412.96 if I round using the 1 that comes after the 6. Okay, so these are just some examples of exponential growth questions that you might be faced with, and we'll have more practice problems to deal with over the next week. But tomorrow's lesson is on exponential decay and how those questions are presented to us as well. Okay, let me know if you have any issues or questions, and don't forget to send a picture of your notes to Google Classroom so I know that you did it. Have a great day, guys.